We start this lecture with an overview, a plan for what will be presented. We'll begin by introducing the bulk of the new forces we will use in this course. We'll start with the weight of an object, the gravitational force near the surface of the Earth, and then move on to discuss the normal force, the force perpendicular to the surface that two objects in contact exert on each other, and the tension force, the force exerted by a taut string. Finally, we will introduce Newton's universal law of gravitation that describes the forces between any two objects that have mass. We will close by introducing free body diagrams, which we will then use in the solution of a Newton's second law problem. In order to apply Newton's second law in physical situations, we will need to increase our inventory of forces. We'll start with the gravitational force near the surface of the Earth. We have already seen that an object in free fall near the surface of the Earth has a constant acceleration whose direction is down and whose magnitude is equal to the constant g, which is equal to about 9.8 meters per second squared. From this description of the motion, we can use Newton's second law to conclude that there must be a force in the downward direction acting on the object, and that the magnitude of this force must be equal to the product of the mass of the object and the constant g. We call this force the weight of the object. It is important to realize the weight of an object is not the same thing as its mass. Mass is an intrinsic property of the object. Its value determines how hard it is to change its velocity. Mass does not depend on the location of that object or on its surroundings. Weight, on the other hand, just tells us the magnitude of the gravitational force that is acting on the object. We will investigate the nature of this gravitational force more fully in a few slides after we introduce a few more straightforward forces. We can use our knowledge of the weight force from the last slide to motivate the need for two more forces. First, consider the incredibly mundane situation of a heavy box sitting on a floor as shown. What forces are acting on this box? Well, certainly the weight of the box is acting, supplying a force vertically downward. This can't be the only force on the box, though, since if it were, Newton's second law would tell us that the box should be accelerating downward with constant acceleration equal to g. Therefore, to obtain the needed zero acceleration, there must be another force that acts vertically upward with the same magnitude. Note that this force is not the Newton's third law pair to the weight, since both forces act on the same object, the box. This force is the force exerted by the floor on the box and is usually called the normal force, since its direction is perpendicular to the surface. What determines the magnitude of this force in general? Well, to determine the magnitude of the normal force in any particular case, we do just as we did here. We apply Newton's law. The normal force is simply what it has to be to do what it does. What it does is to supply a supporting force for objects. The total force exerted by any surface in contact with another surface will always have a normal component, but it may also have a component parallel to the surfaces called the frictional force. We will discuss the nature of frictional forces in the next pre-lecture. Now, a force similar to the normal force between surfaces in contact with each other is the tension force in strings, wires, and ropes. Here we see a ball hanging from a string. What forces are acting on the ball? Clearly, the weight force acts vertically downward. In order to obtain the needed zero acceleration, the string must also be exerting a force on the ball. We call this force the tension force. It exists whenever the string is taut and its direction is along the string, in this case vertically upward. From Newton's second law, we can determine that the magnitude of this force must be equal to the weight of the ball in order to provide the observed zero acceleration. Just as was the case for the normal force, the tension force is simply what it has to be to do what it does. In this case, the string is just holding up the ball. Strings can also be used to pull objects across a surface. In either case, The magnitude of the tension must be determined from Newton's second law. Here we see a ball hanging from a spring. We can use Newton's second law to determine that the spring must be exerting a force on the ball that is equal to its weight. However, if we replace the first ball with a new ball that has twice the mass, we see the spring is stretched more. The spring is now exerting twice the force, but its length has also changed. In fact, the amount by which the length changes tells us the magnitude of the force. The key concept here is that every spring has an equilibrium length, and if it is stretched or compressed by some amount delta x from this length, it will exert a restoring force that opposes this change. The magnitude of this force is proportional to delta x, the extension or compression of the spring from its equilibrium position. Here we see the force law for springs that quantifies this relation. The vector x naught represents the equilibrium length of the spring, while the vector x represents the final length of the spring. The vector difference, x minus x naught, represents the amount by which the spring is either stretched or compressed. The minus sign in the equation illustrates that the force is always in the opposite direction of the vector x minus x naught, the extension or compression of the spring. If the spring is stretched, x minus x naught points away from the equilibrium position. Therefore, the force is directed back towards the equilibrium position. If the spring is compressed, x minus x naught once again points away from the equilibrium position. Therefore, the force is again directed back towards the equilibrium position. Since the force exerted by the spring is always directed towards its equilibrium position, we call this force a restoring force. If we define the origin of our coordinate system to be at the equilibrium position, then our force equation simplifies to F is equal to minus kx. The symbol K stands for the spring constant of the particular spring and is a measure of its stiffness. The units of K are newtons per meter. A large value of K means that a small deformation results in a big force. We now want to generalize our discussion of the force we called the weight earlier. You know that the moon orbits the Earth with a period of about a month, and the Earth orbits the sun with a period of a year. To a good approximation, these orbits are examples of uniform circular motion, and therefore we know that each orbiting body experiences a centripetal acceleration. Therefore, in Newton's framework, there must be a real force exerted on the orbiting body that is responsible for this acceleration. Newton proposed that this force was a universal gravitational force that exists between any two objects that have mass. In particular, he said that any two objects with mass exert attractive forces on each other whose magnitude is proportional to the product of the masses divided by the square of the distance between them, and whose direction lies along a line connecting them. For example, here we see the moon orbiting the Earth. The form for the magnitude of the force that the Earth exerts on the moon, F sub em, is shown. Big G is the universal gravitational constant, and M sub E and M sub M refer to the masses of the Earth and Moon respectively, while R sub EM is the Earth-Moon distance. We know the acceleration of the Moon, A sub M, is equal to the square of its speed divided by the Earth-Moon distance. Applying Newton's second law, we determine the form shown for the acceleration of the Moon. All quantities in this expression were known to Newton except the universal gravitational constant and the mass of the Earth. Newton, however, realized that the known acceleration due to gravity near the surface of the Earth was also proportional to the product of these unknown quantities. In order to make this realization, though, he essentially had to invent the calculus to show that the force the Earth exerts on any object is equivalent to that obtained by simply placing all of the mass of the Earth at its center. Given this result, we see that the acceleration due to gravity near the surface of the Earth is equal to the product of the universal gravitational constant and the mass of the Earth divided by the square of the radius of the Earth. Therefore, we see that the ratio of the moon's acceleration to that of an apple's in free fall near the surface of the Earth is predicted to be equal to the ratio of the squares of the radius of the Earth to the Earth-Moon distance. When we plug in the numbers for the known quantities, we find that this prediction is verified. Newton has shown that the force law that describes free fall near the surface of the Earth also explains the motion of the moon in its orbit about the Earth. Last time we introduced Newton's three laws, which supply the framework we will use to develop our understanding of dynamics. In particular, these laws will for our understanding of the motion of any object in terms of the forces that act on it. In order to use these laws successfully, though, we need to keep careful track of the magnitudes and the directions of all forces acting on the object in question. We will use free body diagrams to accomplish this task. Here we see a man pushing a box across a smooth floor. We've superimposed on this picture a representation of all of the forces acting. Contact forces are shown in red, and the gravitational forces are shown in blue. Note that all of the forces come in pairs, as required by Newton's third law. For example, the force exerted by the box on the man is equal and opposite to the force exerted by the man on the box. Suppose we want to calculate the acceleration of the box. How do we go about doing that? Well, the key step is to realize that the only forces which are relevant to this problem are the ones that act on the box. All of the others can be ignored. A diagram showing only these forces is called a free body diagram for the box. Applying Newton's second law to the box, we see that the acceleration of the box will be equal to the total force on the box divided by the mass of the box. To determine the total force on the box, we will need to add, as vectors, all of the forces shown in this free body diagram for the box. Usually, in order to add these vectors, we will want to decompose the forces into appropriate components and write Newton's second law equations for each component separately. We'll close this pre-lecture by considering a one-dimensional problem to illustrate the procedure to use when solving dynamics problems. Here you see a box of mass m hanging by a rope from the ceiling of an elevator moving vertically with acceleration a. We want to calculate the tension in the rope for any value of this acceleration. The first step is to draw a picture and label all the forces acting on the object in question. Now, in this case, the object is the box, and the forces acting on it are the tension in the rope, T, which points upward, and the weight of the box, mg, which points downward. The second step is to choose a coordinate system. Any system will do, but you will soon discover that choosing one in which one of the axes is parallel to the acceleration will simplify the calculation. Now, the next step is to use your picture as a guide to write down the components of Newton's second law and solve for whatever variable you want to determine. In our case, all of the forces act along a single direction so that we only have one equation to solve. The force in the box due to the rope is T in the plus y direction, and the force on the box due to gravity is mg in the minus y direction. Therefore, the total force on the box in the plus y direction is equal to T minus mg. Substituting this expression for the total force in Newton's second law yields the result that the tension is equal to the weight of the box plus the product of the mass of the box and its acceleration. The final step is to check to see if your answer makes sense. Now, in this case, we just found that the tension in the rope is given by the weight of the box plus an extra part which is proportional to the acceleration. If we consider the case where the elevator is not accelerating, we see that the tension in the rope is just equal to the weight of the box. If the elevator is accelerating upward, the tension is bigger than the weight, and if the elevator is accelerating downward, the tension is less than the weight. This all makes sense. We conclude with a brief discussion of the main points of this prelecture. First, we introduced several new forces. The normal force is the force perpendicular to the surface that two objects in contact exert on each other. The tension force exerted by a taut string is aligned with the string. The magnitude of both of these forces must be determined from Newton's second law in each instance. It is what it has to be to do what it does. The restoring force exerted by a spring when it is stretched or compressed is proportional to the amount of the stretching or compression. The weight of an object near the surface of the Earth is equal to the product of its mass and the constant little g. Finally, forces exist between any two objects with mass. Newton's law of universal gravitation states that this force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Finally, we introduced the concept of free body diagrams, which we then used to obtain the solution to a one-dimensional dynamics problem.